So, after talking about the components we could use for our electrical power subsystem, we want to talk now about the satellite power bus itself. So on top of the power source and the energy storage, we need to add the power distribution and the power regulation. So power distribution means we need to get the power from our solar cells or batteries to our components. And on top of that, our components might not be happy with any voltage they get there. So that's why we need to adjust the voltage according to the parameters of our components. Traditionally, 28 volt of direct current DC, 28 VDC power rail has been used for the first satellites, and that's simply because of the heritage from the aircraft technology. So you had the components that were already in the air, so the engineers just thought like, meh, well, air is air, at least space is space, both buys some sort of and just use the same technology that already works. However, we need to keep in mind that the higher our power is of our satellite, usually the higher should also be our voltage. Why is that? As you can see, our power is calculated by multiplying the voltage and the current. And the higher the current, the higher are the losses in our power cables. And because we don't want to waste so much energy on board the satellite, I mean, we already wasted so much to generate the power. And now if it's already inside of our satellite, we don't want to waste any more power then. And that's why we want to keep the losses really low. We need to increase the voltage for the same amount of power. However, we shouldn't do that above 160 direct voltage, because then we have a very high risk of discharges. We could have an arc that destroys our solar cell. And just to let you know, I again show you a real-life example of a power bus. This is part of the power bus of the flying laptop satellite, the small satellite. Down here you see the unregulated bus, 70 volts. So this is directly coming from our batteries. Yeah? And then we have a lot of interfaces there, interfacing all the different units you can think of. We have some heaters that are fed by 12 volt. So between our unregulated power bus and our output, we have the PCDU, the power conditioning and distribution unit. And this is our regulator. Yeah? We have seen on the previous slide. So we're regulating our DC voltage of 70 volt down to 12 volts. However, we see a lot more components, like the multispectral cameras, MIX. They are not connected directly to the unregulated bus. They have a mixed power unit in between. So for most cases, everything but the heaters and the sun sensors on the lower right, they go on minus 30 volt, I guess. Those other components are fed with unregulated power of 70 volts, up to 70 volts, and have their own power box that regulates the power for the unit. So you can distribute your power unregulated and then have several units to take care of the power conditioning. Those are the two concepts I just want to show you with this plot here. And just have a last look before I move on, how many different voltages we have here on the satellite. This is a relatively small satellite, like a refrigerator. 17, 20, 15, 12, 10, 5, 3.3 volts, minus 5, minus 30. So those are a lot of voltages. Yeah? But in general, we could say, for the regulated bus technology, on the other hand, you see unregulated, For the regulated bus technology, you could use a 3-domain controlled regulated bus. And that means that the regulated bus voltage is controlled either via the sequential switching shunt regulator, it's the SR3, a battery charge regulator, BCR, or a battery discharge regulator, BDR. And the required eclipse power, so whenever there's no sunlight, is supplied by the battery at those times. Batteries, we have seen a lot of different technologies we could use. And the solar power is generated for the bus power and the storage power during the subphase. We have a very simple system. We have the satellite bus that you can get by either the solar array or the battery. But in terms of the battery, we need to take care if we have a charge and discharge unit, and in case we need to dump some of our power because our battery is full, none of our components want to have any more power, but the sun is still burning up there, we need to find a way to get rid of the excess power. This is done by the SR3. In the 2-domain controlled regulated bus, there, with this topology, that controls the regulated bus voltage either by the sequential switching shunt regulator, again, because SR3, or the battery discharge regulator, BDR. So we don't have a BCR unit here. The power is supplied mostly by the battery via the BDR regulator. And in the case of the nuclear power source, the solar array will only be the secondary power source. Yeah? The SGR regulator is required to control the bus voltage if the load demand is lower than the power generated by the solar array. And that means this topology offers the possibility to recharge the batteries without using a battery charge regulator. Last but not least, we have the 1-domain controlled regulated bus. And in this case with a RTG, so the nuclear battery. This topology controls regulated bus voltage via the SGR regulator. Here. The solar array and the radioisotope terminated generator, RTG, are essential power sources here. And the RTG supplies most of the required power through the SGR regulator. And that means the bus voltage is controlled via the SGR regulator. And the SGR regulator is also required to handle any excess onboard solar power in some cases. And that means that the solar array is only a secondary power source. That's the result of it, if you think about it. On the other hand, a small battery associated with BCR and PDR is still needed to supply the required peak power on demand. Now, since we talk about a nuclear battery, it's not so easy to just increase and quickly decrease the power generation of this unit. It's more like a static baseline can be supplied. And again, I have some real-life example here, again from the Flying Laptop satellite. This is a small block diagram of the power conditioning and distribution unit, PCU, where you can see the solar panels connected here, 3 different panels for the 3 panels we have on board the satellite, and we have 3 battery strings on top there. So within the battery we have 3 separate battery strings, and every single battery string is connected to a corresponding solar panel. There's no interconnection there. For every solar panel, we measure the current and we measure the voltage for telemetry purposes, and that goes into our BCR. Yeah? We just had our BCR units. And here we can adjust our output voltage from 20 to 25 degrees Celsius. Moreover, with the batteries, we can decide if we want to charge or discharge the battery. If we have the switch open, we can only discharge because of the diode there. If we close the switch, then we kind of shorten this diode and we can then charge the battery. Again, measuring the current and the current, actual voltage. We have a good set of telemetry to control our PCBU unit. All that goes down into our main switch for some under and over voltage protection and feeds the umbilical connector, our main output from the PCBU. Again, we can measure the voltage and the current, and then it goes into some fuses and other, conditioning cases. In that case, we also have a micro switch, and that is used to switch on and off the satellite. Usually, when the satellite is placed on top of the rocket, you might have a connector that shortens the switch, and the moment the satellite is being deployed in space, then it opens this micro switch, the PCU starts providing power, and the satellite moves up. This is what you use this umbilical connector usually for. But you can also see, you can use the auxiliary power unit for ground testing. Because imagine, you have a satellite in the clean room. How do you get your power? How do you charge the batteries of the satellite? We talked about the depth of discharge. You don't want to discharge your batteries so badly. Just, when it's stored, it's not even spacing. That means you need to find a way to charge your batteries. I doubt that you want to bring an artificial sun into your clean room. You can do that for testing purposes. Huge lamps, they're really warm and bright. But usually, you're better off just having an auxiliary power input, feeding in here over the diode, and then if you close all the switches, from here you can directly charge the batteries. So far so good. We have been talking about the shunt regulator, the BCR and the BDR. I just want to give you a short overview how they could be built up, and then we will conclude for today. This is an example for the shunt regulator for the power level adjustments. You can see different power sources being fed into, again with the diode, and then by comparing the voltage of our bus with an error voltage or some reference voltages, we have some Schmidt triggers that could close some switches, some electronic switches, and you would close the connection over a dumping shunt, or you would dump your excess power over the shunt by closing that towards ground. And if you are above this reference voltage, your negative switches, your MOSFETs there, they are closed, they don't come back, and so there's no connection from your voltage bus over the shunt to the ground. And for the BCR and BDR, well, they both use very similar concepts, and I think we don't need to go too much into detail. Just remember, it's a oscillating process. You have an oscillator, and usually you would also have an electronic switch, like a MOSFET up there, and some filtering, and for sure a coil, a big induction coil to stabilize the voltage, and then usually, unfortunately I don't have a pen here, but it doesn't matter. You could, by dynamically switching on and off of your switch, let me approach it that way. The moment you close the switch, you charge your coil, and it goes up. And then you try to discharge your coil. So all the output being fed now by the coil, and it decays. But instead of letting it decay to zero, you switch it back on and recharge. And by dynamically switching on and off of the coil, you basically can decide where you want to land with your voltage level. Yeah, just by simply the duty cycle to be on and off. And in order that the voltage doesn't drop to zero in those phases where you don't close the switch, you need this coil. But if there are some specific questions, please email me. We can go into detail if you're really interested in that. That's no problem. But well, I don't want to scare you off at this early stage from all the electronics stuff. But imagine simple electronics can have a very big effect on our satellite. And to conclude for today, we have an example of a small satellite. Imagine you have the structure of your satellite, you define it, you have your 50 kilogram satellite, volume of a small refrigerator, with different solar panels, 4 body mounted there. After you define the structure of the satellite, you go into your satellite orbit. So by having the satellite and the solar panels where they are, you can go into your satellite orbit, and with the satellite orbit and your design, you can have a graph and check on the generated solar power for 1 year. And you see, this is anything but linear. It's fluctuating over the year in many dimensions, not just for the sun phase, but also for the rotation and the total power output. And you can see down here on the lower right top, our required power is about 35 watts. And we have the sun phase and the eclipse phase. And just to account for this eclipse phase, we need to install a much higher power on board of our satellite of more than 60, around 65 watts peak power in terms of solar panels, just to account for the eclipse phase. Keep in mind, we only wanted to have 35 watts of average power. Yeah? This is going to be part of one of our exercises we're going to have later, to actually have some nice and neat calculations and get more into detail on that, so that you at least did it once for yourself and see, well, how much overhead you pretty often need to install. And again, I want to conclude with the last image from the flight laptop satellite. Maybe you can sit down back home and think about this for a moment and really let it sink through, to understand the principle of the power subsystem of board of the satellite. And we see with the blue color the battery charge in percent. So the lowest discharge you can see here is around 97% to 100%. We have the temperature of the PEM. It's a camera system in degrees Celsius. So imagine whenever the temperature goes up of the camera, it's probably in operation. We have the solar panel current with the dashed line and the total current of the satellite, both in amperes. Yeah, and then look at it. So first, there's some solar panel current coming in, and here it's immediately goes to zero, probably eclipse phase. You can see that immediately the battery charge starts to drop. So now we're feeding our camera, for instance, or whatever, or the satellite bus itself, by our batteries until the sun is back. We have another solar panel current, and we start charging our batteries again. Until it is completely charged, then our maximum power point tracking, for instance, sets in, reduces the amount of power drawn from our solar panels so that we don't overcharge our battery, and it continues like that. Yeah? just take the time, have a look at it, and try to understand what the satellite is doing there. Try to imagine the scenario the satellite is going through here within those 3.5 minutes. No, I think it's 3.5 hours. 3.5 hours. In that sense, I would like to conclude for today. We were looking at an electrical power subsystem for satellites and spacecrafts. We were looking into batteries and solar panels and different technologies we could use. We had a short look into how a satellite power bus is being built up, what are the components and the topologies we could use there. Please don't hesitate to ask any questions, and well, have a good one.